Hey guys, welcome back. So we're going to be talking about solubility equilibria now. So there's a couple things that we'll be talking about in terms of solubility equilibrium. One of which is how to predict if something is soluble or not. So solubility equilibria has a lot to do with this KSP that we just talked about. So that's solubility product constant. Because ionic compounds are strong electrolytes, they dissociate completely to the extent that they dissolve. But not everything completely dissolves. And so that's why we occasionally find that things crash out of solution. Okay? The other thing is that these things tend to be temperature dependent. So depending on what temperature we're at, we may be able to get more or less into solution. You've probably seen this, because if you raise the temperature on water, you can dissolve more salt or sugar in it. Okay? If you lower the temperature on water, you can dissolve more starch, more cornstarch. So that solubility goes up as the temperature goes down, which is typically not the way it works, but that is an exception that we see, okay? Now, when our equilibrium equation is written, the solid is on the reactant and the ions are the products, and that's because we want something that we can work with, okay? If we were to write this as Pb2 plus 2I minus, crying out loud, 2I minus, going to PbI2 solid, and we're trying to write a K for that, then our S doesn't appear, so then we'd be 1 over that Pb2 plus times the I minus squared. And because that's sort of unwieldy, we tend to write it in the other direction so that we know that when we write it, that PbI2 solid is going to give me a Pb2 plus the 2I minus, and that KSP is then going to be the Pb2 plus times the I minus squared. Okay? For me, that's easier to see. And the other thing is that I know that even though this thing is insoluble, some amount of that is going to go into solution. That's determined by the value of K. So the bigger that number is, the more I get in solution before it comes crashing out. Right? So that's something that we talk about with that. Okay? So our KSP is always equal to the product of the ion concentrations raised to their stoichiometric coefficients. So because I have 2I minus, that has to be squared. So there's nothing else that we see there, okay? So that's what my KSP is going to look like for any of these things. Awesome. I know how that works because I can write equilibrium constants. So that shouldn't be a big deal. But that implies a lot of things, okay? One of the things that it implies is that we can do the same kind of mathematics with KSP that we've done with other things, all right? Let's first practice by writing some KSP expressions for the following compounds. And then I'm going to have some that I'm going to put up on D2L for you guys so that you can try them on your own. Now, I want you to try these on your own right now, but this is what we're going to be talking. Okay, so I'm going to give you a couple of seconds to try and process that, and then I will go ahead and write those out for you. Okay, so silver chloride. If I want to talk about silver chloride, we're going to talk about AgCl. I'm going to assume that that's a solid, which it is, and we'll talk about that being a solid later. We're writing a KSP, so we assume that it's a solid to be able to write a KSP. That comes apart to give me an Ag plus ACl minus. That KSP is then going to be equal to Ag plus times Cl minus. And again, it's a 1-to-1 relationship. Both of those are raised to the first power, so that's what we're looking at there. When we talk about magnesium hydroxide, Mg is a 2 plus. Remember, he's an alkaline earth metal, so he's a 2 plus. That means I need 2 OH minus to make that balanced. That's a solid. When that comes apart, I get an Mg2 plus 2 OH minus. And again, these are aqueous over here. I get a little lazy and I don't always write them. So KSP for that is going to be the concentration of the Mg2 plus times OH minus squared. I didn't give myself a lot of room, so unfortunately I had to write that down below. When we talk about the chromium 3 hydroxide, let's go ahead and give ourselves some more space. So chromium 3 is a Cr3 plus, right? Because that's what that 3 in the parentheses means. So that's a Cr3 plus, and it's a hydroxide, so I know that I'm going to have an OH minus. So when I make that solid, that's going to be a CrOH3 solid. That will then come apart to give me a Cr3 plus, which is aqueous, plus 3 OH minus. That KSP is then going to equal Cr3 plus times OH minus to the third. Okay, so that's how we come up with that one. Now, again, I'm going to put these on D2L for that set. When we talk about lead iodide, so lead is a Pb2 plus. Okay, now if I didn't know that and I wrote it as Pbi, that would be okay because there's nothing that tells me it's a 2 plus. So I can write it as Pbi, right? Because it would be looking at Pb plus aqueous plus an I minus aqueous would give me a Pbi. Now I happen to know that it's normally Pbi2, but again, this is fine. And the reason that that's fine is because I didn't tell you that lead was 2 plus. So you can write that as Pbi because we have to assume that the charge is 1 because I wasn't told what it was. Okay, so that would be a perfectly fine reaction for that. KSP in that case would then be the Pb plus times the I minus. Okay, now, okay, and let's talk about barium sulfate. So barium sulfate, awesome. We're going to do barium sulfate. Now, barium is a 2 plus, and sulfate is a 2 minus. So when we put that back together, that's going to be a BaSO4. And that's a BaSO4 solid. Okay. KSP for that is still going to be Ba2 plus times the SO4 2 minus. Okay. So that's going to be those expressions right there. Now, like I said, I'll put the rest of them up on D2L for you, but that's practice writing K expressions. The big thing with KSP is to make sure that we know how many ions we need to make that thing net neutral, okay? And so that means we need to pay attention to things like chromium 3, because that tells us what that charge is. Otherwise, it's based on where they are in the periodic table. So on my alkali metals, are going to be a +1. My alkaline earth metals, actually, no, I don't have one. My alkaline earth metals are going to be a +2. So those are things that are going to tell me that. Remember, all of my middle metals can be any number of different charges. The only other one that we really know 100% is aluminum, which is a 3 plus. Okay, so based on where it is in the periodic table, that's what we're going to be talking about in terms of charge. Okay, so those are writing your KSP expressions. Now, I said that we would figure out how we know what's soluble and what isn't in a little bit. Now, my students are familiar with this set of rules and that they're applied in order. I know other teachers use the table to predict things. So it says if you have this metal with this anion and you look over and you see, is that soluble, insoluble, whatever. Those will be available to you on the test. Okay, so that table will be available to you on the test. I may ask you things about these solubility rules, though, on my tests. So I want to make sure that you're aware of that, okay? So here are my solubility rules. Salts of group 1A and NH4 plus are soluble. Now, give me 2 seconds because I really need to find a periodic table to be able to do this. So pull one up. It's going to give me what I need. Yes. Okay. So, pull this over here. We can talk about this too. And group 1A, that's this group right here, my alkali metals. Those are going to be soluble. NH4 plus, also being a single charge. Those are always going to be soluble. So if I have an NH4Cl, that's soluble. If I have an NaCl, that's soluble. KCl, RbOH, any of those things that are +1 in that first group right here, that alkali metal group, those are going to be soluble. Things that are attached to a nitrate, NO3 minus, a chlorate or a perchlorate, so a ClO3 minus or a ClO4 minus are soluble. So any of the metals that are attached to those polyatomic cations, anything that's attached to an NO3 minus, a ClO3 minus, or a ClO4 minus are soluble. Okay. When we talk about our halogens, right, these guys right here, anything that's attached to them is going to be soluble except Ag plus, Hg2 plus, which is mercury 1. So since there are two of them, each one of it is a +1 charge. That's how that appears. It always appears as a dimer. It's a weird thing. Pb2 plus and Hg2 plus. Okay, so mercury 1, mercury 2, lead 2, and silver 1. Those are not soluble. Sulfates are soluble except for BaSO4, PbSO4, so Pb2 plus, Ba2 plus, or Hg2 plus, so HgSO4 is not soluble either. OH minus are insoluble except for these guys right here. So anything that's in this first group, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, francium hydroxide, all of those are going to be soluble. And of course, water, HOH, is going to be soluble. BaOH2 is also soluble. Okay. As far as carbonates, phosphates, and sulfides, S2 minus, those are not going to be soluble. So those are insoluble. And of course, these rules are applied in order. Right, okay, so what the hell does all that mean? Well, that's a good question. So let's take a look at some things that you might get asked about. And one of the things I'm going to pull up again periodic tables so that we can see that. And then I'm going to pull up the solubility rules that we just had. Sorry, I gotta find the right file. I hate it when I do this. Okay, so hopefully that will work for us when we're trying to look at this. All right, so let's see. PBI2. Is PBI2 going to be soluble? Well, all right. So is it a 1A or NH4 plus? No, it's not. PB does not fall into that group. Is it an NO3 minus, ClO3 minus, ClO4 minus? No, it's not. So the next row says chlorides, bromides, iodides are soluble except, and one of the things that's in that list is Pb2 plus. So this PbI2, not soluble. And this is not soluble because of rule number 3. Okay, so that row says that PbI2 is not going to be soluble. AgNO3. Well, Ag is not a group 1 metal, so it's not an alkaline earth metal. So then I look at the second row. It says NO3 minus are soluble. So this one is soluble, and that's based on rule number 2. Okay. NIS. Okay. Ni happens to be over in here. Where the heck is I, by the way? He's right there, number 28. So he's not an alkali metal. All right. When we look at the next one, we are NO3, ClO3, ClO4 minus. None of those apply. Cl minus, Br minus, I minus, that doesn't apply. SO42 minus is not what we're talking about. OH minus is not what we're talking about. CO32 minus, PO43 minus, and S2 minus are insoluble. So this is going to be insoluble, not soluble. And that's based on rule number 6. Okay. When we talk about Na2S, now, when we talk about Na2S, that's a slightly different situation, right? Because it says salts of group 1A and NH4 plus are soluble. Na is an alkali metal. So anything with sodium on it is going to be soluble. So this is soluble based on rule number 1. Now this is what I was talking about in terms of we have to apply these in the right order. Because if we were to look at the rule that we just talked about, rule number 6, which says that this S2 minus are insoluble, that's not the case here. And that's because that metal is a soluble salt. Okay. So anything that's got that, an alkali metal on it is going to be soluble. Okay, that's awesome. Now, CuClO42. Okay. So Cu is copper. He's right here. He's a transition metal as well. So right now, I don't know much about him. Salts of group 1A and NH4, that does not apply. ClO4, oh, that's right there. It says it's soluble. So this is going to be soluble, and that's based on rule number 2. Rb2CO3. Now, Rb is right here. He's an alkali metal. So that is going to be soluble. Okay, so he's soluble, and that's based on rule number 1. Even though we know that the CO32 minus are insoluble in some cases, that's not going to be true when we're talking about an alkali metal. Okay, NH4 to SO4. Okay, NH4 plus are soluble. So this is going to be soluble based on rule number 1. When we talk about PbSO4, when we look down, we see, okay, fine, well, Pb, where is Pb? Pb, if I'm not mistaken, is right here. So he's a main group element, but he's down over here under carbon. All right, so he's not an alkali metal. He's not an alkaline earth metal. None of these anion rules apply when we talk about the sulfates. Chlorides, bromides, iodides doesn't apply. SO42 minus is soluble except Pb2+. So since this is listed as an exception, this is not soluble per rule number 4. Okay, now that's what I want you to go through and do for the ones that are still listed here. Again, I will put those up on D2L and walk you through how I made the decisions that I made. But that's what we mean by applying the rules in order and being able to apply those rules, okay? So that's what we're talking about in terms of determining if it's soluble or not, okay? So once we know what's soluble and what isn't, then we can talk about the solubility product, okay? Now, when we talk about the, okay, solubility product, again, KSP for BaSO4, which we know is an insoluble because of what we've talked about before. SO42 minus are soluble except equilibrium constant is KSP is equal to Ba2 plus times the SO42 minus. And that's because there's one Ba2 plus and one SO42 minus. When we talk about barium phosphate, okay, so the phosphates are insoluble. Barium phosphate, Ba3, PO42, we get 3 Ba2 plus and 2 PO43 minus. The KSP for that is going to be Ba2 plus cubed times PO43 minus squared. Okay, so that's how we would write the KSPs for those. Now, Consider that the reaction quotient Q is related to K. Here are the situations that come with that. So if Q is less than K, right? So if my Q is less than K, I don't have enough product. That means that I can keep dissolving things, right? Because I haven't gotten to that point where everything is insoluble, okay? So that's an unsaturated solution. More solid can go into solution, no precipitate will form. If Q is equal to K, then we have reached saturation. So that's our saturation limit. And if Q is greater than K, then that's a supersaturated solution. So precipitation occurs. We have too much solid in there for that to be given, okay? So if you have not gotten to K yet, if your concentration is less than what it should be at K, then no solid forms, okay? So that's something that you may get asked about, i.e. if I have this concentration, will I form a solid or not? So that's something we're going to need to be able to talk about. Okay. Now, what else do we want to? Now, how do I know if the concentration is greater than K per X? We'll come back to that shortly. Have patience, Padawan. We will get there. Okay. That's one of the things that we're going to be talking. All right. So, solubility versus solubility product. So, KSP is a solubility product. So it's not the same as solubility. Those two terms are different, right? Solubility is the quantity of a substance that dissolves to form a saturated solution. Common units for solubility are grams per liter or moles per liter, which is the molar solubility, right? KSP is our solubility product constant, equilibrium constant. So those are two different things. Okay? We can use our KSP to determine the solubility equilibrium, which gives us the molar concentration of the ions. We'll get to that, which we then use from the empirical formula to determine the molar solubility of compound in terms of moles per liter or grams per liter. Okay. So understand that those are two completely different concepts, and we may be asking for either one of those or both. Depends on what the question asks. Okay, so let's make sure that we understand that we're talking about different things. Where are we going next? Calculating solubility from KSP. So, if I tell you that the KSP for CaF2 is 3.9 times 10 to the minus 11th at 25 degrees, what is the molar solubility? Okay, so what we're talking about here, we've been told that we have CaF2 solid breaking down to give me Ca2 plus 2F minus. And KSP is going to be equal to Ca2 plus times F minus squared. And that's equal to 3.9 times 10 to the minus 11, right? We can set up a Rice table for this, just like we did before. Since that solid is a solid, it's not part of that Rice table that I want to talk about. Let me get rid of this for now. Because right now I don't need it, but I need space. Okay, so that CaF2 does not appear in this table. That's why this looks like this. We initially have Ca2 plus as 0 and F minus as 0. When we break down a CaF2, we get 1 Ca and 2 F minus. Okay, so in equilibrium, we're going to be able to solve for that concentration. Now, when I do that, I set my KSP equal to that X times the 2X squared. Remember that 2X, that whole thing is squared. So when we do this, we end up with 3.9 times 10 to the minus 11th is equal to 4x cubed. All right, we divide the 3.9 times 10 to the minus 11th by 4, and then take the cube root. That gives me my x value, which has a value of 2.1 times 10 to the minus 4th. So that's what I see for Ca2 plus. That's what we put right here. But that F minus is going to be equal to 2 times that, because I get 2 ions for each one. And so that means that this is 4.27 times 10 to the minus 4th. Okay. Now, solubility is in grams per liter. So that's 2.4 times 10 to the minus 4th moles per liter, right? Because that's what I just calculated. times the molecular weight of that material, the CaF2, which gives me 0.0167 grams per liter. So as long as the concentration of CaF2 is less than 2.1 times 10 to the -4th, no solid will precipitate. Any concentration above that will give me solid. Okay, so that's what that means. So I can calculate what that concentration is using a rice table. We solve for X. That gives me the value that I need to know to see if it's soluble or not. Okay, as long as I'm below that, then it's going to be soluble. If I'm above that, then I'm going to form a solid, and I will have that solid crashing out of solution. I can also solve for the solubility of that material in grams per liter by multiplying by the molecular weight of that material to know what that solubility is going to be in grams per liter. Okay. Where am I going next? More practice. Now I'm going to take a break here, and I will come back and do some more practice with you in the next video. Okay. So I'm going to stop for here, and we'll talk in a little minute. Thanks, guys.